just like I described some background. Meeting. Okay, fine. Got it. So I'll describe some background of the matrix factorization algorithms, and then I am going to describe the probabilistic model we are going to use, right? And then I'm going to describe this inference scheme. So in this case, probabilistic model will not be exactly tractable because you're learning multiple things at the same time. But the inference scheme here would not be variational inference. So I tried to do actually by writing first down the optimal recursions and try to approximate them instead of going to the Monte Carlo route or a VI route, right? So it's just like something you actually try to do the optimal one, but it's approximate eventually, but it's not VI. So I'll describe just a parameter estimation scheme as well, and then some results and conclusion, right? So this is the problem we try to solve. So we are trying to get a data matrix. So this data matrix is d-dimensional for each observation. Let's say each column is you can think of it as an observation, and there are n data points, right? So this could be describing a lot of things. What you try to do in this matrix factorization problem is you try to reduce the dimension of this data set by learning an intermediate matrix, right? This is like called the dictionary, and these are called coefficients, right? So the rank of the dictionary R would basically, but what you're trying to do here is basically you try to learn a C that is d-dimensional, each column is d-dimensional. You try to run R vectors from which you can construct your observations, right? And then how you mix these R vectors is given by these coefficients, right? So the single observation yk, for example, a column of y, could be constructed if you successfully factorize from the columns of C and the entries of the associated x k vector, right? So this is the problem. So you can see this as like a very simple dimensionality reduction problem, or you can see this as like you can see these things as codes, right? And these things as your observations, and this is just basically the decode, right? If you think about BAE terms. So why this would be useful? I mean, it's just I told that you actually basically reduce the dimension of your data. So for example, here is as an example that the observations are three-dimensional, right? And you try to learn basically a tall matrix. Enables you to reduce the dimension of your data set. So the aim here is to learn both the coefficients and the dictionary, right? And I mean, this is very useful because you could get like high dimensional observations that are sort of, I don't know, frames of a video or audio or spectrogram of an audio signal or any sort of data that can be represented as matrix. Then you could do a lot of stuff once you actually learn the encoding. Here, let's say these are the codes. You could do clustering. You could use it for representation. You can, send the lower dimensional data set somewhere like a communication scenario. You can interpret these if these are interpretable. Missing data imputation is a big application as well, because if there are missing data in Y, actually it's quite easy to handle it. And once you get C and X estimated, reconstructing it is quite straightforward, right? So there are a lot of use cases. I mean, it's used in every area of machine learning. I think one of the most famous ones is recommendation system. So if you have, I think there was a Netflix challenge that was best solved by the matrix factorization, one of the matrix factorization methods. So for example, if these are users versus ratings, right? And you want to predict the rating of a certain user, so you're going to recommend something to this person. It's basically a missing data in your observation matrix. And once you learn your matrix factorization, so matrices, you can basically reconstruct Y, and you can basically predict, for example, what user would use a rating for a certain movie. And there's a lot of applications for genomes and audio signal processing. It's also a big thing in that area. So the most classical approach, I'm going to just basically briefly give some overview, because it's a very old area in many ways. The most classical approach is called NMF. Maybe you heard it, non-negative matrix factorization. And it's basically an optimization-based approach, right? So you just get your data matrix and you put C and X and you minimize this norm, right? And the name non-negative comes from the fact that, so you can do this in multiple ways. You can do classical gradient descent on C and X, right? Alternating gradient descent. Actually, there are algorithms doing that, but that wouldn't ensure non-negativity. So the original paper put a lot of emphasis on non-negativity, which is something I don't care about. But they argued that if you ensure that C and X are both non-negative and your data is non-negative as well, let's say image Let's say these are like each column of Y are images, for example. Let's say you have a face data set and stuff like that. They basically derived an algorithm that looked like this. So they derived it's based on gradient descent, but they chose a step size in a very special way so that they get multiplicative updates. So these divisions, and I think the multiplications are element-wise. So dividing two matrices. But eventually this algorithm became very famous, right? Because, so this was, I think the paper is in, was it Nature? It has been cited, I don't know, 14,000 times already. And then there has been a lot of follow-up work doing similar sort of matrix factorization methods. So you can easily imagine the cases where you regularize X, you regularize C, you want X to be sparse and stuff like that, right? So those people have done all of that. So some milestones are basically, this is Francis Bach and Julian Myra. They did this online optimization version. So obviously the original paper was assuming that you store your data set, right? And you use it for every update of C and X, which is kind of costly. And then people, it didn't take much long. It actually took a long time for someone to develop this, right? So people just started using stochastic gradient-based approaches because if you can actually decompose this for a business norm as a sum over the columns, right? There is no difficulty. So then you can subsample and do stochastic gradient descent. So how did this come here? Right. And and people have done also the probabilistic version. So what probabilistic versions are, I'm not going to write down here, but you can easily imagine you can think of this as defining an implicit Gaussian, right? Because it's a log of Gaussian basically. So you can just write a probabilistic model and then put priors on C and X. So for example, the simplest version of this was in this paper, they just put IID Gaussian priors on every entry. And then you can try to do posterior inference. What you can do, you can sample from posterior of C, posterior of X, and you can sample also from predictive distribution in order to predict an entry. And you can, arguably in this case, you would have some uncertainty around your estimates, right? That was the motivation. And also like the classical, one of the good works, I think was, one of the classical works was actually these updates also were interpreted in a way that it comes naturally out of some VI scheme. So you can put forward the probabilistic model for which the NMF updates are actually posterior mean updates. So that was sort of, I guess, an important part of the literature. And also like there was a lot of online inference, right? So also people have done what I want to do, but I'm not going to review that bit because there's not much, there's nothing very similar. So what we want to do here is we want to do the probabilistic ones, right? We want to still have some prior over C and X, and we want to get like posterior probability measures over C and X. We want it to be dynamic. So this one difference is that I want to basically consider a case where Y, let's say, is a time series or is a Markov process, or it can be like in the natural scenario, it could be a spectrogram of an audio, which is time-dependent signal, or it can be a video, right? Every column is an image. You vectorize the images, and your data matrix has some sort of time dynamics, right? So I want to have a dynamic version of this, explicitly considering that Y is a Markovian process. And I also want to have a scheme that's sequential, which means I want to basically get like Y1. So that's the notation, right? Y1 is the column, first column of Y. So I want to get Y1 and I update C1 and X1, right? And then I get Y2 and I update C and just the second column of X. So I don't have to revisit anything. I just go like sequential, right? That's the aim. So that's one of the big motivations of the work that you do it purely sequential way. Okay, so what I'm going to do is I'm going to put a structured prior on C, right? Because if you want to update C in an online way like this, you cannot update. You put the prior on C, you put the most general prior on C. It's not going to actually work out well. So we are going to put a structured prior on C. We are going to assume very general nonlinear dynamics on X, right? Because if you look at again this structure, if Y is a Markov process and you try to reduce the dimension of Y into C and X, it's very natural that you actually have to model X as a Markov process, right? Because if X is a Markov process and C is a matrix, then Y is going to be, there's one way to reduce the dimension and still learn the time structure. And as a result, I'm going to basically, I'm going to give the model, but the general idea is to use an exploit stuff like column fit, right? Because that's like very well studied and it's quite stable. Okay, so the model is given like this. So it is in many ways a classical state space model, right? So if you ignore the first part, and these three distributions are just like the regular state space model. It is a regular state space model with a nonlinear evolution here. And this nonlinearity is parameterized by theta, right? Which is one of the things we want to learn in this setup as well. But then the likelihood is just given like for each yt, you have a c times xt. So, I mean, the relationship is quite clear, right? Because if you sort of, your model postulates this, you basically implicitly postulate this, right? This is going to hold if you actually learn CNX or estimate CNX. Then there is the other advantage of this sort of model is there is going to be a quite flexible nonlinearity here, so you can actually put your ideas about your data set into F. So if your data set, let's say, a periodic time series, obviously you want to reduce the dimension of it. It makes sense to have the latent process or the latent states evolve in a periodic way, right? You're just going to postulate a model depending on what you think your data is. And then the inference on this model would return probability measures over CNX, right? So one of the things I will not write down matrix normal distribution because it has a complicated form, which wouldn't give any more intuition. But the only thing you need to know for matrix normal for now is that C0 is the mean, right? So I just have an initial mean. And these two matrices basically are row covariances and column covariances, right? So what I assume here, what I meant by structure prior in the beginning is I assume that rows are uncorrelated, right? So they are independent, but columns can be correlated, which makes sense because I want to learn a dictionary that are each column of the dictionary is an element of the dictionary that you can reconstruct your data points. So it makes sense to learn some sort of structure between them. Also, it's quite convenient computationally, as you will see in a bit. Okay, so this is the model, right? It looks complicated, but it's just, if you ignore C and theta, it's just a hidden Markov model. I mean, I don't know how many people remember these conventions, but like this is for these double circles for the observed data, right? And circles are for random variables, and square is for a static variable. So theta, we don't have a prior on it, which that's why it's square here. So this is the model basically. So what I'm going to describe now is how would you do optimal inference in this model, right? Like if you were to calculate any integral you want and you had infinite computational power, there is an optimal inference recursion. For fixed theta, I'm going to describe. And then I'm going to describe how I approximate these things, right? What I'm going to use a tractable, I call tractable approximations where there is no sampling, right? And then once you actually, so the procedure goes as follows. You basically, if you are able to do inference with fixed theta, you can do parameter estimation trivially, right? Because you can do it outside the loop using marginal likelihood, again, approximation. Okay. So if you were to given just a model like this, which is the very generic version of what I described before, right? For fixed theta, how would you do inference? So this is the question. Only difference, again, between this and a state space model is we have this C, and this C connects all the observations to each other in some way. So in order to, I mean, in general, like this is like a general way to look at these things. If you want to derive sort of like a one-step exact inference, if you want to derive an exact inference recursion, what you do is you actually derive one step of it, right? Because, for example, if you are given these distributions, you assume, and you actually figure out how to update these things into y1 to k here, and then p of xk, y1 to k there, you actually know everything, right? Because if k is 1, this corresponds to prior. So if you actually know how to update one step update from here, then you actually can do exact inference. So that's the question. So if we are going to assume that we have these things, and we are going to look at if we can actually figure out the update first. So in this case, the first step is easy, right? So if you basically have it's not an optimal. So if you basically have these distributions, the first thing you would do to predict xk is just to integrate over the transition model, right? It has nothing to do with C. So what you would do is the first step is you get the predictive distribution. So you basically put your previous, this is called the filtering distribution. You integrate out the xk minus 1 and you get your predictive distribution. So this is just not something difficult, right? So we know, for example, if this is a Gaussian and this is a Gaussian and linear Gaussian, let's say, then these are exact. These are like Kalman prediction rules. If this is nonlinear Gaussian, which in our case will be the case, then you can just use extended Kalman prediction step. You can use other stuff as well, right? I just tried extended Kalman, but it's general. So in order to, so now I have this predictive distribution. I have to update, right? I have to incorporate observation here. And now I also have to go back and incorporate observation into this distribution. So I condition on y1 to k rather than k minus 1. So I have two update steps, one of xk and one of c here. So first, I'm going to look update of c. And in order to do this, you basically need to compute this double integral. And the reason is, if you look at how to update c, right, this is just a basic classical Bayesian update written in a recursive way. So there is this kind of distribution, which is going to act like the likelihood, right? And it's given by another integral. And then you have the marginal likelihood, which is actually a double integral. So you integrate this once more. Right? You can see the difficulty. I mean, there's a lot of difficulty because you have this integral might be intractable. This is certainly intractable. And also, even if these are tractable, you might have forms here that actually doesn't allow you to compute a closed form update, right? So tractability is not the whole problem. Actually, this one is going to be tractable, but the form of it will not allow us to actually implement this exactly, right? So the coefficients update is, so the update of xk from the predictive distribution I showed before is also quite easy. So you have this sort of update, which is again a Bayesian update. I mean, if you were to do normal filtering without C in mold, you would have this update, right? You wouldn't have this k minus 1 to k minus 1 part, and this would be rather simple. But now we have this dependency all coming through C because we integrated C out. So this term is basically another integral, right? So these are what we would need to do if we actually wanted to do optimal inference, right? So these integrals are computable. That's not very good news, but because these are going to be like resulting Gaussians are going to have some form. Surprisingly, it's not actually going to allow us to do this update exactly. So then what can we do, right? Approximate inference. So we start from the same point. We just say, okay, we have some approximations. Let's say even if these are exact, we will, like in one step, they are going to become approximations. So we just assume that we have some good approximations to these two distributions. And prediction step is sort of easy. Why? Because I told again before is the prediction step is just the same as a nonlinear filters prediction step, like an extended Kalman prediction step. So in this case, for example, I just described the extended Kalman case. Obviously, you can do a lot of different things. Extended Kalman update is easy because you just get the mean of the previous posterior distribution, you pass it through your nonlinearity, and you propagate the covariance using these Jacobians, right? And these Jacobians you can compute using automatic differentiation. So that's it. Like you can have a procedure that's completely black box. So you just give f theta to this function, and it's going to give you the mean and the covariance, right? So this is kind of simple. So now it's going to come to updating. I think I changed. Let me see. Okay, but I first describe the dictionary, so it's fine. Okay, so given that this is easy, so now I am going to look at the update of C, right? Because if you actually remember the previous recursions, update of C and update of xk are actually kind of independent, so you can't do it in any order. So I'm going to first update C here. So in order to derive the approximation of the update of the C, you just like, again, remember that we had this form, right? P of C. So the C, the difficulty here. So the difficulty here is, let's say you want to update C, which is a matrix, right? So the classical way to do this would be vectorize the matrix, get a huge covariance matrix, and update the huge covariance matrix, and then form your matrix again, right? This would be like the way to go. But this would be horrible, right? Because first of all, D can be 2000, you can have an image. And R can be 40. Let's say you have 40-dimensional subspace, your rank is 40. This is going to be something horribly, the covariance matrix of this is going to be like 20,000 times 20,000 or 40,000 times 40,000, right? You don't want to do this. So what we want to do is we want to preserve a form like this. So we assumed initially this is row covariance, this is D times D, and this is column covariance, this is R by R, right? So R is quite low, like it's a quite small number. It maybe 10, 40, I don't know, 100 at most maybe. If you were to able to do actually the posterior form in the same form, so I have a posterior that preserves this form, right? Which means I can only update V's, and I don't have to deal with this D times D part. I don't have to form a huge covariance matrix or anything like that. I can only store R times R covariance matrix for columns, and I can update my mean, right? So this would be quite easy for us. That's what we are trying to do. So we actually have to try to have matrix update. So I actually never have to form the vector version of C. I update C in a matrix form. And as a covariance propagation, I only update R times R, this matrix, which is, of course, super cheap, right? So compared to what you would have to do otherwise. This way, so if we actually manage to do this, we are going to only have this R times R updates. And the other ways wouldn't be possible. So in order to derive the updates, we write the vectorized form, right? We never actually do the vectorization, but in order to derive the updates, you actually, when you write down the matrix normal as just a distribution on vector, it actually comes out like this, right? You have a vectorized form of C0, and you have this massive covariance. This is V Kronecker product identity, right? So yes, can you exploit the special structure in this covariance without actually ever forming C? And the answer is yes. I mean, if you actually do, so remember the update of C. This is the update rule of C, and this is the integral that you need to compute this likelihood, right? You first compute this likelihood. So this is this likelihood appears in the update here of this integral, right? So you can actually compute this integral because this is a linear Gaussian distribution, it comes from the model, and this is the predictive of xk, which is kind of just Gaussian with mu and covariance, and this distribution is just like computable in closed form. But the problem with this, so let's say we know this, right? It's quite nice. We go back and plug it here. I know that this is a Gaussian. Can I actually update this in an exact way? It is not possible because you can see that C appears in the mean and in the covariance, right? This makes it quite difficult. So if C wasn't here, this was pretty simple. You know how to update this. So it appearing in the covariance, it makes it actually impossible to have an exact solution. So here is approximation idea is quite simple, right? Okay, let's do the convenient thing. I just want to replace the C in the covariance with something approximate. And then from then on, it's quite simple for me to update C, which is I'm going to show how. So the first approximation here is just you plug here the previous value of it, right? That's it. But you leave the mean intact. And one more approximation here is that you have to approximate this somehow in a diagonal form. And I'm going to show all of why we are doing all of this in the next slide. But we are not stopping here. We actually don't want to have full covariance here. We actually want to have the closest Gaussian with diagonal covariance. And this is actually computed like this. So all you need to do here, from here to here, is you compute this trace term divided by D, and you form your whatever diagonal Gaussian approximation, right? So these are like mean field VI, basically, but not actually explicitly doing VI. So all the reasons, the whole reason of all of this is, remember what I wanted to do. What I wanted to do is I wanted to have a matrix variant Gaussian. So this is just a vectorized notation for it, the same thing. I want to have this form, and after update, I want to have the same form, right? So I wanted to do this because then it's quite cheap for me. And if you have a Gaussian of this form with a diagonal covariance, and C is here not vectorized, but you can actually write it as a linear map on vectorized C. So that's the same thing. That's the whole trick, actually. You can actually get an update of the posterior mean, so this one, in purely matrix form, right? So that's actually possible. So you can actually just update VK. This is an R times R matrix update. and this is your dictionary, whatever, something times dimension of the data times 40 or something. You can basically keep updating these matrices as a proxy or as a sort of approximate way to update your posterior mean and covariance without ever forming these huge covariance matrices, right? So this is the whole point of all the approximations I was driving so far. So this is actually quite fast. If you implement this, it's really, really fast. So this is how you update C, right? So once you get the prediction from the prediction step, you did the extended gamma filter or a prediction or any other prediction, you just do these two steps in order to update your dictionary and the covariance of the dictionary, right? So the algorithm sort of slightly emerges. You have the prediction step, you have these two steps, and now you have to update from this prediction you have to posterior of xk, and the algorithm is done, right? You're given the algorithm. So all is left is basically you get the C update. Now you want to update xk, the posterior of xk from the prediction. And it's just the same problem. We run into the same problem, right? If you recall, so this is our update rule for xk, and we have this kind of likelihood, which is an integral again. And this integral is computable, but you have the same problem. So if you look at this integral as a sort of likelihood, you have this linear map of xk, which is nice. We like linear Gaussian systems, but xk also appears in the covariance with a quadratic form that's actually making it impossible to go back and exactly write down this update rule. So we use the same trick. What we do is we replace the xk's with the most recent approximations. That's mu. So I only replace it on the covariance, but I leave it on at the mean because I need to leave it somewhere, I guess. So if you have this kind of likelihood, now the update is actually just the Kalman update, right? It's very simple. I mean, because it's just a linear map of xk, going from prediction to update these are just Kalman update rules. They look complicated, but this is just standard toolbox of Kalman filter, right? So the algorithm then is you do the prediction, you do the matrix updates, and you do these updates, and this is all you do. So you never sample anything, and you don't have to deal with any sort of other approximation. Right? So of course, there is the problem. You actually go too back. Anyway, there is the problem of estimating the parameter, right? If you look at the model. So I described you for fixed theta. I described you how to update xk given an observation. I described how to update c after the most recent observation. Now, of course, you need to fit theta as well because that's arguably one of the most important parts of the model. So how are we going to do that? So we are just going to use the standard MLE techniques, right? So it's just get the marginal likelihood, get the logarithm of it because of computational convenience, and update somehow describe a scheme that converges to theta star, right? So there are two ways to do this. First is going to be, let's say n is small, because actually in many cases, more cases than you can think of, n is quite small, right? You have a quite short data set because I don't know, it's time series of something you cannot observe a lot. So one way to do this is iterate over this. So you actually form your estimate fixed theta, form your estimate for like running the filter from 1 to n, and update theta outside of the loop. And the other one is if you have like a very, very large data set and you just do it purely online, right? I'm going to show both cases. So this is the iterative case, by which I mean you actually fix your theta at theta I, and you run all the filter that I described, the update steps for fixed theta, and you obtain this log marginal likelihood and approximation of it, which I will show in the next slide. What is the approximation? Once you actually build this approximation of the whole sequence, which can be done like just running the forward filter, because you can build these things iteratively. So you don't have to store all data or anything like that. You can just keep summing as a running sum, right? Basically, once at the end of iteration, you are given an estimate of this, and then you update your theta, and you do the same thing again. Right? That's the outside. So one more thing that the model gives us, all the approximations anyway, is a nice approximation of marginal likelihood, which is also closed form, right? So remember that this was the approximation I made. I made the diagonal Gaussian approximation to this distribution, and then I actually approximately obtained a posterior of this, right? So if you use these two distributions, there are other options in the model actually, because there are different approximations for different things. But if you use these two distributions, you get like a marginal likelihood approximation, right? Because the integral over C, multiplying these two and integrate over C, is actually analytically tractable, and this is the resulting, well, log likelihood, right? So this is a Gaussian. One of the nice things about this is now it is, I mean, if this was 10 years ago, I would stop here, right? I wouldn't try to there, like putting here a very complicated model and then try to derive the gradient and actually implementing it. But now you don't have to care, because you just code this function and you can just differentiate through it. And there is no sampling or anything like that. So it's like a deterministic function given your mu k minus 1 and I don't know, parameters ck minus 1 and so on. So you can compute the gradients quite easily. Or any f you want to basically use. And finally, the last algorithm is just basically if you have a very long time series, you don't want to do this theta update every outside of every loop, right? You can basically use this kind of online estimation scheme. Instead of doing gradient descent on the whole marginal likelihood, you can just use this most recent marginal likelihood. This is not exactly, it's not true in the sense that even if this was exactly computable, this scheme is not really guaranteed to converge in theory, but in practice people use this and it sort of works. Okay, so what are the experiments, right? So these are the algorithms. This is all update rules I described were actually giving you the algorithm. And of course, if you have any questions, maybe that's a good moment to ask. Otherwise, I'll just go on with like some experimental results, right? How can you use this kind of idea, and why would it be a good idea to do this for this and so on, right? So for example, for the synthetic case, so we wanted to just have a synthetic example. We just simulated data, right? Because it's the first sanity check we all do, I guess. So we just formed a periodic subspace model. So this state connected through sort of like a phase information in some sense, and then we had the periodic component. And we just choose to create a 20-dimensional data set, right? D equals 6, so 20, and we choose to decompose it into 6 components. It's again an arbitrary choice. And we chose basically a parameter. Why do I have 6 parameters? Oh, because so you know that xk is a 6-dimensional vector, right? What we did actually not clear here is for each dimension we chose a different frequency, right? So you have a 6-dimensional. I mean, if you remember, X is like a wide matrix, and each column of this matrix is modulated by a different percent. And okay, what do? We want to use this iterative version because we simulated slightly shorter data set. Again, it's not written here, but what's the short data set? We want to learn all of this, right? We want to learn C, we want to learn X corresponding X's, and we want to learn these parameters, which are the frequencies. So this is how it works, right? It kind of works well in this example. So this is like the blue one here are the X columns of X plotted like, sorry, rows of X, sorry. So each of these are rows of X plotted over time, right? And you can see that blue ones are the real ones that we simulated, and red ones are the estimated ones. So the estimated frequencies of the theta fit really well. And C was generated randomly. So actually, I'm not going to show C because C has, there are many C's that fit the same sort of representation. But what happens is you can see the predictions, right? So these are, the blue ones are the observed data, and the yellow ones are the unobserved data. So the algorithm didn't observe them. We just predicted, we just constructed these red predictions from the last point, right? So the model was fit well so that you can actually simulate forward as long as you like, and you still predict very well, right? Of course, this looks impressive because the data doesn't look anything like the periodic data. But once you know, like there's a periodic structure underneath, you can actually, of course, do this, right? That's not very surprising. I mean, it's nice, but it's also not super surprising, I would say. And we tried to do the same thing on a real data set. So obviously, real data sets are always smaller, mostly in these cases. It's lower dimensional. So for example, in this case, we have this Beijing air quality data. It's just 439 observations, and it's just 3 variables, right? So it's not a high dimensional problem in some way. Anyway, we reconstructed this sort of model. So sorry, we postulated this sort of F. We said, okay, it must be actually possible to learn this three-dimensional data set just using one function, one x. So we said r equals 1, right? This is like an extreme case in some sense. And it was indeed possible because if you, for example, if you compare this to a random walk model, so we postulated this model and this model. This basically says you have some subspace that moves like it's random walk, right? So there's no dynamics. So you need, you need to know at least if C is doing all the job, right? You kind of need to test whether actually this makes sense, whether putting f theta or not putting anything. So this is what we did, right? So these are each 3 dimensions of the data set, and you can see that in the random walk model, the predictions are just flat, right? So C is not doing all the job basically here. So C basically translates the coefficients into, you can see the fit is nice when it's observed, but there's nothing when you actually try to predict. But here it actually does the job pretty well, right? So if you predict forward with f theta, it actually does follow the true dynamics. This was one of the, I think, nice results. So we try to do like different applications. So one of the things you can do with this is basically change point detection, let's say. What we try to do in this example is, again, I think 20 dimensional here. Yeah, so we have 20 dimensions of a time series, right? We have a change point somewhere, but here. But the change point or the change only happens in 3 dimensions. So this thing changes, this changes, that changes, but the rest of the data doesn't change. We still try to estimate the change points. So it's a very challenging scenario because like 17 out of 20, they don't have a change, but you still want to detect the change, and you do it using our model. So the idea is to reduce the dimension of this time series in such a way that you actually see on the coefficients on x's, there is a change, and you can detect the change on a much lower dimensional scenario. Because if you run your change point detection on this data, it's never going to give you the correct change point. So what we did is we tried to actually build a GP model. I think some people like GPs. So we tried to actually, can I go back? So we tried to build x's, which are the rows of the second matrix, so the coefficient matrix. We modeled the rows of x's as GPs. How would you do this in this context? Obviously, we used the state space representation, right? So we actually took a modern GP. We wrote down the basic state space representation. That's an SDE, right? And we discretized this SDE. So that's our model of the subspace, right? And so what does the features look like? So basically, so these are the real change points. These are, of course, just plotted to see. And if you actually plot the x's, you do this using our algorithm. One thing to notice, there are no parameters here, right? We just set this parameter, so there's no theta in this example. If you actually reduce the dimension, then you can see kind of the change point actually appears quite naturally in the low dimension space, right? So the idea here was, okay, what's the difference between running the change point detection on the whole data set, right? You choose your favorite change point detection, and then run the same change point detection algorithm on the features. And is there an improvement? And that's the improvement, right? So these are the contaminations. So we actually contaminated data with T noise. So that's actually quite a bad contamination. That's why all algorithms fail. And this is sort of close to Gaussian. What you do, you can see that if you run on the data, you get like 76%. But if you actually run on the features, it's 85%, right? And this other algorithm, because of the outliers and so on, this is a quite famous one, multivariate Bayesian online change point detection. It's called, I think. That's actually quite bad compared to even this naive algorithm, I would say. So this was the improvement basically in change point detection case. I think this is the last one. Yeah. So these are just numbers, the type you put in your newspaper, or AI stuff in this case. But this just showed basically, so these are the benchmark algorithms there. You can see this is temporal matrix factorization. This is probabilistic matrix factorization. This is something called Bayesian probabilistic matrix factorization. If you basically compare, and if you run the algorithms and compare, this one as a imputation task. So it wasn't actually prediction. It was you run all your algorithm forward towards until the end, and then you reconstruct the missing data using your CNX that you learned. And this is the MSC. I think it's the MSC on the left on the missing data set. So there are 2 algorithms that I didn't explain. So I explained the first algorithm to you, but there is a robust version where the likelihoods are T distribution. So it's basically handling outliers better than the naive version that I explained. And the runtimes were quite low, although eventually with all the parameter fittings and so on. So the advantage of, for example, you can see the runtime is not much higher, not much lower than this, but this is purely online, right? This actually stores all the data. So this is on a small data set, there is not much difference, but if the data set was huge, basically that would be a huge difference. So we didn't try actually that regime. So, and these are the uncertainty coverages. It's not very important. In some sense, it's important. So if you actually predict, if you actually use the uncertainty, so we can actually build the distribution of the missing data. We can actually have a covariance as well, right? We impute with the mean, but we have the covariance. And you can see where the real data, because we remove data ourselves, you can test if the real data actually is in the coverage of the 2 sigma uncertainty, right? And in this case, for example, let's say this example, 92% of the data points were in the range of around 2 sigma bar, compared to this MLE method, which estimates C with an MLE estimate. So there is no prior on C. Actually, prior on C makes a difference, right? So in this case, there is no prior on C. So C is estimated with an MLE method. The coverage actually much lower, right? In many examples. So even though if you estimate C with an MLE and you can reconstruct a predictive, uncertainty bar, prior on C somehow affects things, which is another nice point of this experiment. Okay. So, I mean, the whole point of the talk was basically this Kronecker structure was very important, right? So you assume P of C has a Kronecker structure and you develop things in such a way that this structure is preserved. So that was like actually what gave us this quite speedy algorithm. And the other important bit was all the extended Kalman stuff, updates were basically possible because you just like compute the Jacobians and so on using automatic differentiation. And again, gradient descent on basically this marginal likelihood, which I derived by hand, but I only derived the marginal likelihood, not the gradient of it, right? So this was again possible using this automatic differentiation. And actually, despite I showed you the gradient descent updates, I actually used in some examples, I used Atom, right? So you can just plug and play with different optimizers in this case. And I told you also like we have a robust version, which has T likelihoods. So I mean, there are like multiple, I don't know, some of this you can see quite easily, right? So F theta we used interpretable F, like mainly periodic F that I showed you, because it's the easiest way, like you can imagine your data you can interpret. But there is no reason why you cannot use a neural network if you have a reason to do so. Also, it's one of the obvious uses. You can actually have physics-informed version, right? If you have like a high-dimensional data set and it's a good reason to decompose it in a linear way using a linear map, and you assume that your low-dimensional space is moving according to a physical rule, and it's quite easy to extend this to physics case. And also, what you can do is you can get, instead of like a single Markov process, you can have switching Markov processes, which is quite useful if you want to model activities, for example, like your data set somebody's running and somebody starts walking, right? You want to actually know the switch, which you can model with this kind of ideas. This is the citation, yeah, and I think that's all. These are the references. Okay, you leave it here. Any question? There is a. I was checking if there are people. Yeah.
Is there any relation between this and like a probabilistic numerical method?
Yeah. So, I mean, the motivation was sort of coming from that direction. I would say this update. Only relation is not actually a useful one. It's actually a superficial one. Is that this update is quite similar to, if you actually have a matrix C that is symmetric, this update is quite similar to the quasi-Newton update. I don't know if you can see the relation, but then there this thing is 0, right? It's called the Broyden update, I think. So that's why I saw this in the original literature, or actually I saw this update for a symmetric matrix in the probabilistic numerics paper. And and that was the moment I actually thought that I can use this for matrix factorization, right? Because so that there is a relation, but not actually not a direct one, I would say.
Would this like represent like the uncertainty to do with your new? Yeah, I'm not sure like what the uncertainty maps to, because you know how in probabilistic numerics it's meant to be the uncertainty associated with the numerical method.
So that would be
like,
so.
What does this uncertainty represent? A similar thing, do you think?
I mean, in the original paper, this was the inverse of the Hessian, right? This update, and this was the uncertainty associated with it. But here, I think there is no. I mean, I'm not trying to reproduce a classical numerical algorithm here. So this is kind of what I'm doing. Eventually, in many ways, I'm just doing filtering somehow, right? But only difference between classical filtering and this is that in classical filtering, you assume that you know your state model. So there is a real model that you know. I am trying to extract a model here, right? I'm trying to say, like, I'm going to extract a cosine. It's not that I know that it's generated by a cosine, right? So that's kind of, this is kind of like an unsupervised machine learning perspective on the same sort of algorithm. Should know this thing. Yeah.
How do you posit the dynamics? Like,
so that's, yeah, I mean, that's a very obviously craft, so art, I would say. So here, I mean, the examples only have been, so this is like a synthetic example, is a cosine, right? And this is the only sort of real example where actually we predict the future. And this is again like a simple cosine model here. And in the imputation example, we just use that random walk actually, which the difference is because we don't want to predict the future, we only wanted to predict the past, let's say. So random walk model was good enough to actually impute in a meaningful way. So we actually didn't do any modeling, you know, in any real sense of the word. But I guess it would be really nice to see if you can actually use this in a real application where you actually have a reason to think that the f is certain function, right?
Or like a neural net, I think.
So neural net, it would be nice, but again, I guess like one appeal of this is you actually can write down a certain f you can interpret like a cosine. So this is nice. In the neural network case, it's all black box, so you can use as well something else.
I guess estimation in that case will also be quite.
Yeah. I mean, I think one of the nice applications here is if you have actually, as I said in the end, switching case. I think it's quite natural here because if you have activity recognition data, which is one of the applications of time series, activity sort of changes abruptly, and then you need to actually model it in your F, right?
Yeah, you can play around with like some sort of heteroscedastic.
Yeah, exactly. Yeah. That would be really nice. Yeah. Or you can try to run like a switches. You can try to run multiple. So that's what we try to do with a friend, that you can try to have switches. So you have different Markov processes, and you try to estimate switches with a particle filter and stuff like that. So you.
I guess there's that whole like time series literature which we could explore.
Yeah.
Like see like some sort of moving average type model.
Yeah.
So you should play
Exactly. Yeah. Exactly. So that's the nice thing. You can actually play with any F you want, right? So the code we have actually for this, we have GitHub repo where you can actually get the code and replace your F and run the algorithm. So that would
implemented in Python.
Yeah, it's most of it is Python. One of the experiments is in MATLAB, but the rest is in Python. So yeah.
I have a bunch of other questions.
I just wondering, so you mentioned like two main tricks.
Yeah.
So the economic structure, the covariance,
Yeah.
and the not-of-line differentiation.
So you mean the replacing the covariances?
So like the evolution, I think, yeah, the other one was something with the parameters, the fact that you chose to optimize the mathematical like
This one.
I think that this line before that. So that was was that one of the conclusions? But like because one was that you mentioned that you exploited the economic structure.
Yeah. So that's, I mean, also the sort of there are very similar papers, but the purely online. So this is the fact that this is actually purely online. So at any time you only store a single data vector. And that's actually kind of apart from the optimization versions, there wasn't, at least to my knowledge, there wasn't a probabilistic one that actually has just purely online version, right? So there are ones that use Markov process on the factors like the X, but they all do sort of batch inference.
Yeah, my question was more about like do you have any intuition about why would, like, for example, if you were to choose a different kind of optimization scheme, like a different grade, like you would take a gradient with respect to different functions instead of one, like what? I'm just trying to understand, like, which of these two kind of tricks that you used play the most
made it work.
role?
I don't know, because I guess like so we implemented this without the parameter estimation bits in some applications. That was working quite well as well, and we didn't try just with parameter estimation. So I don't know. I mean, in this case, the marginal likelihood actually worked surprisingly well. So this was like eventually a very good approximation. So I don't know which one. I think the C update. So instead of optimizing C, so I don't know exactly. Okay, where is the C update? So this update, the other algorithm I implemented, so that's actually we compared to this MLE SMF I showed, right? So that's not an existing algorithm. That's just an algorithm I invented to compare this. Like that's an algorithm in itself. So if you actually don't do this, fix C, and just optimize C with respect to some gradients, again maybe marginal likelihood, that's actually so much worse and so unstable. It's actually very surprising to me, because so for me this was actually one of the ways I changed my mind. I said, okay, doing the Bayesian stuff, people think that this is actually not optimal to do it, and it's just pain for no reason, right? But it wasn't the case, because this V matrix sort of like a preconditioner from the right? So that's just not a precondition. So if you take the gradient of basically the log likelihood, these terms except the V all appear in the gradient, right? And only thing the C update gives you, the Bayesian update gives you compared to gradient descent, it gives you this preconditioner from the right, and it gives you this division, right? Whatever that means. So these two terms makes all the difference. I mean, it changes completely how you train. So that's why I think one of the nice things about this is you could actually, of course, not put a prior on C and try to not do this. It's not for nothing. It actually changes a lot. If you just update C, it's hard to train. If you just try to do gradient descent on C and you don't have any uncertainty around it, it changes two things. It's basically much harder to train for some reason. The other thing is I showed the coverage much worse, right? The uncertainty coverage actually gets worse. So I would say this is the most important bit of the whole algorithm. So if this didn't exist, then there would be nothing like to show, basically, I think. Yeah, this is there is a proof of this in the paper.
I think we probably have to wrap up there, because I know that another group is coming in.
Okay.
In this
Okay.
room in the next 10 minutes.
All right.
Thank you.
All right. Thank you very much. Thanks.